To wrap up today, let's think about what we achieved from a data structure point of view, and then I'll tell you why you should care. So multidimensional data, there are interesting operations you can do on it, like what are all the objects inside this subspace, often rectangular. There's the nearest operation where you can say what is the closest object to a specific point, and you can generalize that to k nearest. Now the most common approach to this is some kind of spatial partitioning. We showed this uniform partitioning approach where you break space into lots of little boxes. We showed the quad tree approach where we have basically a generalized version of a binary search tree where you have 4 different neighbors, and each node owns 4 subspaces. And then we saw the KD tree, which was a generalized k-dimensional BST, where every single node has 2 subspaces, and as you work your way down the tree, you cycle through all the dimensions of your data. Now, spatial partitioning, the reason it matters is it allows you to prune the search space as you explore. And so far we've just kind of seen these kind of silly, dry examples. So let me show you some more cool examples. I'm going to play some YouTube videos. Hope we don't get any copyright strikes. Let's see how it goes. So the first is, let me show you the murmuration of starlings. Okay. So here's some darn birds flying around, doing their thing, living their bird lives, and look at them go. All right, it's pretty exciting. Here they go. Yeah, and I've seen grackles doing this in Texas, but it's not nearly as impressive as these starlings. Okay, so here they go. They're just flying around. Look at them. They've each got their own plans. They're flapping their wings, living their lives. Okay, nobody's crashing into anybody. That's pretty nice. It's kind of mesmerizing to watch. It's like very cool. All right. So those are real starlings doing real murmuration. And so let's see a little simulation. So it turns out that there is a pretty simple algorithm by which you can simulate almost the exact same behavior. Like, it's kind of amazing to see how close it is. So these are fully synthetic starlings. And here what you'll notice is there's this other kind of bird flying around. You can see it occasionally. It's a hawk chasing the starlings. And that's why they're kind of freaking out and pulsing as they're dodging this predator. There's a hawk. And so it turns out there's a very simple set of rules. Let's see, we call them the Boyd simulator. That's what they're called. There's a basic set of rules, which is steer to avoid crowding local flock mates, steer in the same direction as others, steer towards the average position. And you can also add issues like obstacle avoidance or seeking goals, and that's what we just saw. And so it turns out that in order to efficiently simulate starlings, they need some way to find their nearest neighbors efficiently. And so I've written a Boyd simulator. They call it Boyds. That's just what Craig Reynolds called them because it's how you might say bird in New York. And I think that's pretty cool that you can recapitulate this feature of the natural world, this idea that birds have this emergent behavior. And KD trees or quad trees are a great way to do that. Another example is NBI. So in Project Zero, you had a quadratic algorithm. Every object had to calculate the force on everything else. But that's very silly if you're doing large-scale actual physics simulations for practical purposes, or even just for fun. So for example, you do not need to calculate the force exerted by each individual star in the Andromeda galaxy as it pulls on the sun. It's better just to treat the entire Andromeda galaxy as a single object. But how do you know what to do? I mean, in that case, sometimes the answer is obvious. You can draw the line in advance. But let's say you have a very complicated simulation where maybe the sun gets launched into the Andromeda galaxy, and now you need to actually calculate the individual forces. How do you smoothly do that? Well, one optimization is known as Barnes' Hut. And the basic idea is you treat the universe as a quad tree of objects sorted by space. And if a node is sufficiently far away from X to the point where you don't need to think about all the individual forces, well, then you can treat that node and all of its children, because it's hierarchical, as a single object. So if we think of the Andromeda galaxy as very far away, effectively what this allows us to do, and I'm kind of hiding some details here, but it allows you to treat the Andromeda galaxy as a single object for the purposes of interacting with our sun. So this is a visualization built by some random guy named Cody Husky. And he's just basically showing how quad trees are happening under the hood, and you can see this gravity stuff going on. And I'm not going to talk about this in any great detail, except to say, hey, this is Barnes' Hut in action. It's pretty cool. You can see the quad trees getting drawn. And I find this stuff really particularly fascinating And I only wanted to get a little bit of a sneak preview in 61B because this is something that you'll see later if you go into this. But hopefully I've inspired you a little. And so that's it for today, and I will see you next time.